All right, now we get to talk about that Monte Carlo pi program where we use random number generators to give us an estimate of pi. This is fun. So first off, I want you to think about the absurdity of talking about random numbers on computers. You know, a lot of people just take it for granted. They call the standard stock rand routine and they just like, oh, I got a random number, that's cool, off I go. But wait a minute. Computers are deterministic machines. They're a bunch of binary switches. How do you do a random number on a computer? Yes, we can sample white noise, but that's a hardware solution. How can you write a program that gives you a random number? It's actually very, very challenging to create good random number generators. And you need to care because there's a lot of statistical methods out there where people use random number generators to sample a problem and from those samples generate an answer. And I hate to be so pessimistic, but a majority of the methods that I've gotten deep enough in to look at the code and see what they do, where they're using random number generators in a Monte Carlo algorithm to drive towards an answer, the majority of cases where I've dug into the code, they've done it wrong. Now, that's not that's an anecdote. It's not a global sampling. Maybe I've just, happened to work with bad programmers. But the majority of the cases where I've gone in and looked at it detailed, they did it wrong. So I think this is something where it's worth your while to not only learn about thread private variables, but also to spend a little time learning about what you need to get right for a random number generator. So just to remind you of the problem, we're going to throw darts at this figure right here. And if the darts land inside the circle versus outside the circle, I'm going to keep track of that. And that ratio gives me the probability of them ending up inside the circle, and that will be equal to the ratio of the areas, which is pi over 4. So that's the basic program. And here we have the basic program. Now, if you think about it, it's easy to parallelize because that loop overthrowing the dart is just really easy to parallelize. So I just have private for the x and y, where I estimate the x coordinate and the y coordinate of the dart. So I just make those private. And then I'm going to count up how many times they land inside the circle. So that's where the if x squared plus y squared is less than the radius squared. All right? If that happens, they fell inside the circle, I increment that counter. So it's as easy as can be. All right? And I do that as a reduction. So I don't have to put any other fancy synchronization around that because it'll happen. The reduction will take care of that for me. Very, very easy program. All right? Now, just to give us something to work with, I created an easy random number generator. Those of you who are hardcore random number people, I know this isn't a great generator, but the thing is the code is very simple. And this is the full code for the random number generator. It's called a linear congruential generator, and that's all the more I need to say about it, other than you just see it's real simple. I have a multiplier times the random last value plus an addend, and then I take the modulus of the whole thing, and that gives me a random value. The key is I have to save the last random value to use in computing the next. So that's the key. It gives me a sequence of pseudo-random numbers. And so it keeps track of who's the last one I computed. And so we always talk about seeding a random number generator. You have to tell it where to start. That's what we mean by seeding a random number generator. So I looked up good values for the multiplier, for the addend, and the modulus, and that gives me my random number generator. All right? And this is the code for it. And it's very, very simple code. It's as easy as it can be. That gives me a simple random number generator. Okay, so now I ran this code. And you can see in this picture here, what I'm plotting is the relative error versus the number of samples. And I've done it in a number of cases. First off, I did it with one thread. And then I did it with 4 threads, tried it once, 4 threads, tried it again, 4 threads, tried it another time. And what you can see is as I run it again and again, I get different answers. Same number of threads, but each time I run it, I get a slightly different answer. Not only that, the answers have higher errors than if I ran it with one thread. All right? This sucks. So what's going on here? Well, one thing that's going on is if I do that simple parallel version of the program where I'm calling the random number generator, it's not thread safe. All right, think about it. One thread calls it, it's got a random last value. Next thread calls it, what random last does it pick up? Who knows? It's a race condition, it's a mess. Okay, so the number of threads, as I call with a different number of threads, I'll get different answers. It's a race. It's because my library routine was not thread safe. So how do I create a thread safe version of it? What I need is each thread to have its own copy of random last. Now, I could do this by passing into my random number generator a parameter to keep track of the last value it computed. But remember what I said, you can't change the library interface, which, by the way, that's how real world works. You're given a math library, you can't go through and change the interface. So as you can see, the easy fix to this was to make it thread private. So by putting pragma OMP thread private random last, each thread has its own last value, and now it's thread safe. Now I should get consistent answers each time I run it. And sure enough, right here when I go and run it, I get consistent answers, the same answer every single time that I run it with a number of threads. But the answer still has a higher error. If you look at the large number of samples route, once we get past the early chaotic range, I'm still not converging to an answer as good as I got with one thread. What the heck is going on? This is so important, even though it's about numerical analysis and not about OpenMP. I really want you to bear with me and go through this here. I want you to think about it. With a random number generator, I seed the generator, and I'm picking out a sequence of pseudo-random numbers. So my blue bar here is the universe of possible pseudo-random numbers given a particular generator. All right? So now I'm going to go through, and in a typical problem, I pick a subset, depending on my seed. I seed it at one point, and then I get a subset. That's what that blue line represents, the dark blue line. Well, now think about what happens when I go to a multi-threaded situation. Each thread, by whatever means it chooses, seeds the random number generator. It picks a different pseudo-random sequence. What if those pseudo-random sequences overlap? Or why wouldn't they overlap? If I'm randomly picking some new seed, so each thread gets its own different seed, why won't they overlap? And what happens if they overlap? That means I'm oversampling a section of my dartboard when I'm throwing those darts. Well, that's broken statistics. I get worse answers, and that's indeed what's happening. If I'm not very, very careful how I seed my random number generators so that I have provably non-overlapping sequences, then I can get reduced statistical quality out of my answer. This is so important because how many of you who've ever looked at these sorts of programs have seen someone do some simple computation over the thread ID, and that gives them their seed? And then they go off and they're like, oh yeah, everything's fine. No, everything's not fine. If you don't go to great lengths to make sure that those sequences don't overlap, you're screwing up your statistics. And that's when I said that most applications I've seen that do serious production level science with random number generators get it wrong because they ignore this point. How do you fix it? Well, I'm going to tell you how to fix it. But before I go there, let me say the right way to fix it is hire a pro. Okay, it's really hard to get random number generators right. So Intel has a math library package called MKL, and in MKL they have provably correct parallel random number generators. So spend your money, go buy someone who does it, buy something that does it right. But if you're kind of like me and a do-it-yourself kind of guy, there's a way around this, all right? The way around this is to use something called, well, there's several ways. One way around it is to use something called a leapfrog algorithm. Now, the leapfrog method uses modulus arithmetic, and it's a different arithmetic system, but what it basically says is that one thread will get, let's say you have 4 threads, right? One thread will get one value, then it'll jump 4 ahead to get the 4th value, then it'll jump ahead to get the 8th value, it'll jump ahead to get the 12th value. The next thread, it'll get the first value in the sequence, then it'll jump ahead the number of threads to get the 5th value. It's basically that cyclic distribution. And I can go through and modify the formulation of the linear congruential generator so it does that leapfrog. Now the beauty of this is I have one seed and I do the leapfrog. I have a non-overlapping sequence, but here's the other thing that's cool. Is the pseudo-random sequence I generate is the same regardless of the number of threads, which is very handy for debugging. And indeed, when I do this, you can see that regardless of the number of threads, 1 thread, 2 threads, 4 threads in this table, regardless of the number of steps, the number of darts I threw, you can see I get exactly the same answers regardless of the number of threads. So that's what you get with the leapfrog method. Now, I want to emphasize, though, that from an OpenMP point of view, the key was thread private so that I have a thread-safe library call. And if you did that in your exercise with the PyMC, you got the right answer. Kudos to you. Excellent. But to go to the next step and get a numerically correct random number generator, you had to do something to make sure you didn't have overlapping sequences. And that gets a little bit trickier, and that was with that leapfrog method I just showed you. So take a look at the code on the leapfrog method. I don't want to take too long to talk through it right now, but it's a really nifty way to solve this problem. So I hope you enjoyed walking through thread private and enjoyed this slight little diversion into parallel random number generators.